Good day everyone, my name is Akaru Mezwabi from Nigeria. In this video, we shall design a simply supported one-way solid slab, which is part 3 under one-way solid slab. You can make reference to the design steps, which is part 1 and part 2. Kindly subscribe to our channel and stay tuned for more videos on reinforced concrete design.
Good day everyone, today we shall be designing a simply supported one-way solid slab. In our previous class, I talked about the design steps. Right now we have a question on the board which says, design a simply supported one-way solid slab of 2.5 meters by 5.2 meters with a mean weather condition. Take live load as 3 kN per meter square with C30 concrete. The first step we need to take from our solution is our initial proportioning, which is the initial sizing of the slab. This is the preliminary sizing before we get our final sizing. With this initial sizing, we will later check in our deflection to see if this sizing will be appropriate or not. So by looking at this, we are having 2.5 meters by 5.2 meters. Then we have to check the Ly over Ls ratio, which is 5.2 over 2.5 and is greater than 2. That means we have to design this slab as one way. Then note, when designing a slab, you consider 1 meter by 1 meter. Then this should be your length and your breadth. Your breadth should be 1 meter. You consider 1 meter by 1 meter portion when designing a slab. So the next step is to get your effective depth, which is D. And your D is your span, your shoulder span, over your basic ratio times modification factor. You can take your modification factor as 1.3. Then your basic ratio, you can get it from table 3.9, BS 8110. Get your basic ratio from there, BS 100. For simply supported, your basic ratio is 20.
The basic span over effective depth ratio for rectangular and flank beams are given on table 3.9, BS 8110. To get your ratio, you check for the support condition and the type of what you are designing for. Like I said earlier, you design a solid slab as a rectangular beam. This is the rectangular beam, cycled. And what we are designing for is simple supported slab. So if you are to choose, you consider the rectangular section and the simply supported. Then your ratio will now be 20. Same as others. If you are designing for cantilever, continuous beam as well, or slab.
Then that gives us 2.5, converting it to millimeter, which is the LS at the shoulder span, over 20 basic ratio times multiplication factor. That gives us 96. So let's approximate to the nearest inches. So take D as 100 mm. Then the next thing is for us to get our overall height, which is H. Our overall height, which is H, from the end to end, which is overall height H, and D starts from the middle of reinforcement to the end of slab, while D prime is the half of reinforcement plus cover. That's D prime. Our overall height H is D plus cover to reinforcement plus diameter over 2, which is this. Then your D, like I said, take it as 100 mm. Then your cover of reinforcement to 25 mm from table 3.3 base 810. Then you can get your cover. For to get this cover, we only consider the durability, which is the exposure condition. And our grade, we are using grade 30 concrete.
To get your nominal cover from table 3.3, according to the question, we are only considering the mid weather condition under condition of exposure and grade 30 concrete. So to pick your nominal cover, this row and this column where they intersect, then your nominal cover becomes 25 mm.
So from table 3.3, you can get your cover as 25 mm. Then your reinforcement for a slab, your main reinforcement, you can take it as, it should not go below 12 mm. So we are taking 12 mm as our main reinforcement. That gives us 100 plus 25 plus 12 over 2, which is 131 millimeter. So we can approximate our H, which is our overall height, to 150 millimeter. So from this now, we can now get our final effective depth. Since we have already approximated this H to 150, from there we can now get our final effective depth. So since our overall height is 150 mm, our D now becomes our final effective depth from initial proportioning. Although at the end we may still end up checking if this is sufficient. D becomes H minus C, which is the cover, minus reinforcement diameter over 2, which is 150 minus 25 minus 12 all over 2. That gives us 191 mm. So the next step is our final proportioning, which is the loading. So the next step is our final proportioning, which is our loading. To get our ultimate load, UDL, is 1.4 GK plus 1.6 QK. This is our dead load, and this is our factor of safety for dead load. While this is our life load, QK, and factor of safety 1.6 for life load. Our dead load in this design comprises of the self-weight, which is the volume we are considering, multiplied by density of concrete. Density of concrete is 24 Newton per mm square. Partition allowance and finishes can cover for others, which are considered in this design. Our life load, like I said earlier, is the function of the building, or the function of what you are designing for rather. We are taking our life load here as 3 kilonewton per meter square. So for us to get our ultimate load, we have to get this value, then input them into this to get our ultimate load. So from there, we can get our dead load as a GK. As our self-weight, which is the volume times density of concrete. So it's, this is the overall height multiplied by the length times breadth. Like I said, we take 1 meter by 1 meter portion. Then multiply by the density of concrete. That gives us 3.6 kilonewton per meter square as our self-weight. Then our partition allowance 2.1 kilonewton per meter square, and finishes 1.2. So our total dead load becomes 6.9 kilonewton per meter square. Then our life load 3 kilonewton per meter square. Then from this, we cannot get our ultimate load.
Good news, good news, good news. For those who have interest in practicing software on reinforced concrete design, and those who want to further improve their software skill on reinforced concrete design, Grand Maya Nigeria Limited now offer an intensive visual and physical software training on reinforced concrete design. The good thing is that we can now go visual and physical. That means we can reach out to you worldwide. Also, Grand Maya Nigeria Limited do steel and reinforced concrete design and detailing. We deliver worldwide. For more information, kindly reach out to us via call on WhatsApp on +234 81 35 65 3805 or email us at admin@grandmaya.com. Thank you.
Then our ultimate load now becomes 1.4 multiplied by dead load plus 1.6 multiplied by the live load. That gives us 14.46 kilonewton per meter square. But the code states that when designing a slab, you design it as a rectangular beam. That means we have to cancel out this square to make it 14.46 kilonewton per meter. So to cancel out this square, we have to multiply it by 1 meter. And that gives us 14.46 kilonewton per meter square multiplied by 1 meter, which is 14.46 kilonewton per meter. So that's all for the loading. We can now move to the next step, which is our structural analysis, our bending moment. To get our bending moment for a simply supported beam is WL square over 8, which is, this W is 14.46 kilonewton per meter, and this L is the LS, the shutter span, is 2.5. Which is 2.5 square over 8. That gives us 11.3 kilonewton meter. From our free body diagram, at the end of the support, we have 0, 0 bending moment, while our maximum bending moment occurs at the middle of the span, which is this place. That's where our maximum bending moment occurs. So this is the critical section when we are designing the middle of the span. That will be our critical section when we design it. So take note. Then we can now move over to the next step. So the next step is to check for our K value. K, which is maximum bending moment over characteristic strength of concrete, multiplied by the depth, multiplied by the square root of the effective depth. If it gives us 0.156 or lesser than that, we design for only tension reinforcement. That means compression reinforcement is not needed. It's like this. By looking at this is your compression zone and this is your tension zone. If a load is applied, this top tend to experience compression, while this bottom tend to open, experiencing tension. Look at it, tend to open. This simply means that if K is lesser than or equals to 0.156, we are only going to provide tension reinforcement at this place. That will be sufficient to keep this slab in position. That means this tension compression reinforcement is not needed. That means the tension reinforcement that will be provided at this place, this is the critical section, will be sufficient to keep this slab in position. So we can now proceed to check the K value. Yes, if K is above this value, we have to design for both compression and tension reinforcement. So let's check for K so we know the formula to apply. So from there, our K is, which is the maximum bending moment, 11.3 to convert to Newton per mm, multiplied times 10 raised to power 6 over characteristic strength of concrete multiplied by the breadth times the square root of the depth, gives us 0.03, which is lesser than 0.156. That means compression reinforcement is not needed for this design. Our reinforcement area for only tension reinforcement becomes m over 0.95 fyz. This our Fy is the characteristic strength of steel, which is which is 460 Newton per mm square. Take it as for high yield steel. Then Z is LAD, lever arm, multiplied by the depth. This is your effective depth. LA is 0.5 plus 0.25 minus K, which is this, over 0.9. So we have to get the area of reinforcement, which is our area required. So from there, our lever arm, which is LA, now becomes 0.5 plus root of 0.25 minus 0.03, which is our K, over 0.9, gives us 0.97. If your lever arm is greater than 0.97, take it as 0.95. It should not be greater than 0.95. That gives us 0.95. Then our Z, which is lever arm multiplied by the effective depth, now becomes 0.95 multiplied by the effective depth, which gives us 113.05. So our area required, which is maximum bending moment over 0.95 multiplied by characteristic strength of steel multiplied by the effective depth, now gives us this. So our area required for tension reinforcement is 228.7 millimeter square. From our table, we provide Y12 at 250 center to center of reinforcement.
To get your spacing from area for bar spacing, there are two things you consider: the bar size, which is the size of reinforcement, 12 mm, which we are using, and the area we got from our design, which is 288.7 mm square. So from this row, which is 12 mm, you pick your area from here. The area to be provided should be higher than this area we got from our design, but the difference should not be that much. So this one, we can go for either of these three, but the higher the area, the lesser the spacing. So we can go with this one, 52 mm square. Then you trace to the top to get your spacing, which is 250 mm. You can also do this for the distribution bars as well. So we are providing Y12 at 250 mm center to center for our main reinforcements, and the area provided is 452 mm square.
So from our table, the area we provided is 452 millimeter square. Now the next is for us to get our distribution bar. For a one-way slab, you only design for the shorter span. Then for the longer span, you only get your distribution bars reinforcement. That distribution reinforcement is the minimum reinforcement, which is 0.13% of BH. So to get your distribution bar, which is your minimum reinforcement, is 0.13% of BH, which is 0.13 divided by 100 multiplied by 1000 mm multiplied by your overall height, everything in millimeter. That gives us 195 millimeter square. Then from your table, we provide Y10 at 250 center to center. Area we provided from our table becomes 314 millimeter square. Then we can now move on down to the next step, which is our deflection check. The next step is our deflection check. we have to check the allowable span over effective depth and the actual span over effective depth.